কোন ডিপার্টমেন্ট নিয়ে the purpose কি physics physics department নিয়ে the material synthesis one thing. I will not take today much time, but just I will explain. Yes, today also I explained one technique. Okay, so convert analog filter to digital filter. One technique I explained, that is impulse invariance method. Okay. Now another very important and most widely used method is bilinear transformation. In the third module, we discussed that Butterworth, Chebyshev, and other filter in analog domain. So this was the first step of designing digital filter, that you have to have in the form of analog transfer function, analog frequency response, and after that by suitable conversion method, you have to get it into digital transfer function, the transfer function in digital domain. Okay. So there are many techniques. So one technique was this impulse invariance, and another approximation method. Another one is impulse invariance, and now this one is bilinear transformation. So the earlier methods had some disadvantages. So impulse invariance method has had disadvantage that the whatever the analog frequencies are mapped, okay, in digital domain, uh, they are mapped as many to one transformation. Many to one means low frequency is mapped easily to low frequency or that same frequency, but high frequency or very high frequency are not mapped accordingly. They are also mapped to low frequencies. So that effect was called aliasing effect. Now this bilinear transformation overcomes this method, that the mapping is not many to one, it is one to one. That means one particular frequency in analog domain is mapped into one particular frequency in digital domain. Okay. So digital frequency is not continuous, it is minus pi to plus pi. So within that, okay, the analog frequencies are mapped in one-to-one fashion, not many-to-one fashion. Many-to-one fashion takes place in impulse invariance method, and in bilinear transformation, the mapping is one-to-one. Now let us see what is the basic concept. So, and it was discussed in today's morning class that uh, the left half there is mapping of the points in the S plane, okay, to the points in the Z plane in some expected manner, like the left half S plane all the points in the left half S plane is mapped within the unit circle of the Z plane. The right half points of the S plane are mapped outside the unit circle of the Z plane. And the j omega axis, okay, the j omega axis in S plane that represent the frequency axis, they are mapped onto the circle, on the perimeter of the unit circle. Okay. So that particular concept was discussed, okay, in the previous class. You just go through the slides. Many of you are not present. Harshvardhan, you are not present. Okay, so you just go through that slides, that what is the concept behind that, and now the same type of mappings happens are applicable here also in the bilinear transformation. So let us first consider that we explain this method with an example. Not it is so-called traditional mathematical analysis. It is explained with the help of some filter function, analog filter function. So this is Hs is equal to B by S plus A. B by S plus A is the filter function, analog filter function. So uh, in S domain, Laplace domain, S domain, Ys, we can write Hs, that is a system function, as Ys by Xs. That is Laplace transform of output divided by Laplace transform of input, that is Ys by Xs, is equal to B by S plus A. It's very simple. Now we just cross multiply across with this equation. Okay, then we get this one, Sys plus Ays is equal to Bxx. Then now taking the inverse of it, inverse Laplace transform of it, we get that it is dyt dt. Sys is dyt dt and Ays is ayt, that is time domain. And Bxs is simply Bxt in time domain. It was S is in frequency domain, now T in time domain. Now how we'll evaluate this equation, this how we'll find the solution. So to find the solution, we use trapezoidal formula. Okay. Trapezoidal formula tells that yt is equal to, if you have the differentiation, that is y dash tau, where dyt dt, then if you integrate with this, we integrate this function within some sample time samples, t0 and tt, t0 and t, with some initial conditions y0, then you can have the formula, approximation formula. So this is the function. Okay. Now, and in this equation, you see that there is some integration formula. So how to calculate this integration formula? So this is actually cannot be done using continuous domain. Okay, continuous domain you can use the op-amp. Okay, analog domain you can use op-amp, but since you have to use the to digital computer, okay, computer cannot perform continuous integration. Okay. So it has to use some special technique like trapezoidal method, a special method. So trapezoidal method is tells that trapezoidal method is what, that suppose we have this the differentiation, that y dash t, okay, y dash t. So we use this yt. Okay, t is, let us say t is sampled at some time instant, t is equal to nt. Okay, and t0 is time sample just before that. Okay, just before that, that means nt minus t, that is the t is the sampling interval. So just before that time instant nt, it is so it is n minus 1 into t. So from this equation we write y of nt, okay, the same, that is equal to this integration. How it is evaluated? Integration means what? It is the area under curve. Okay. Area under curve. So area means area, you see I have written in the right hand side some small note, that taking the average value and multiply with interval. Okay. So there are 2 points. Okay. One point is at nt, another point is at nt minus t. Okay. And since we are taking the curve is what? Y dash, that is differentiation. So y dash nt, okay, plus y dash nt minus t. These are the two different values, and their average value is what? Their average value is divided by 2. Okay, so 2 points, their average value is this. So we get, suppose it is one rectangle. So how we calculate the rectangle, area of a rectangle, that is height into length. Height into length we calculate. So height is the average height. Okay, that is average value of this differentiation value, that is y dash nt plus y dash nt minus t. That is the average value of first and last point divided by 2. That you get the height of the curve. Okay. Then, so height we get, then length. The height and length. Length is t, that is the time interval over which the two samples are taken, nt and nt minus t. So in this way, we calculate the integration, because this is the usual method to calculate in computer. In computer, this way integration is performed. If you use op-amp, then you can directly calculate this integration. But in case of computer, you have to use trapezoidal method. So now the last value is yt0. Yt0 means y of nt minus t. Okay. So now from 1, this is what? dyt dt. Dyt dt means y dash nt. Okay. At t is equal to nt, y dash nt minus y nt. We take this side, minus y nt plus bx nt. So in this equation, we put the values of y and t. Okay, so y and t is what? Y equation to y and t is that value. Okay, that is uh, it is actually y and t is t by 2 into so it is minus a into y and t plus bx and t this side. Okay, so we get y dash and t, y dash and t there, y dash in place of y dash and t. Okay, t by 2. Here you use this equation, y and t is this t by 2, and in place of y dash and t it is this one, minus a y and t plus bx and t minus y dash nt minus t, that is just previous sample with the help of this formula given in 2. So we get this one. So which implies y and t is equal to at by 2. Okay, that is y and t plus at by 2, y and t is minus 1 minus at by 2 into y and t minus t. Okay, that is, we take right left hand side, and we take the output parameters left hand side and input parameter right hand side, bt by 2 x and t plus x and t minus t. So with the notation y n t is equal to yn, that is quantized value, and x n t is equal to xn. So we get this function, that 1 plus at by 2 into yn is minus of 1 minus at by 2. Okay, yn minus at by 2 yn minus 1, that is equal to bt by 2 xn plus xn minus 1. So now you take the Z transform of it. So we get, this is 1 plus at by 2 yn yz, okay, yn minus 1, so that means z inverse would be there, z inverse into y of z, okay, and here xn, that means xz, and xn minus 1, it is z inverse xz. So this way we separate out yz by xz, we calculate yz by xz, then we get bt by t, bt by 2 to 1 plus z inverse, okay, divided by 1 plus at by 2 minus 1 minus at by 2 z inverse. So this is now coming in the form of z, z variable. Okay. So further we slightly rearrange it, okay, and writing in this way, that is b by 2 by t 1 minus z inverse divided by 1 plus z inverse, in resemblance with the analog transfer function b by s plus a. Okay, so just you divide this, okay, with, just you divide, how you are getting, just you divide both numerator and denominator with 1 plus z inverse, okay, you will get this function. And comparing with this analog system, analog transfer function, we can write that s is equal to 2 by t into 1 minus z inverse divided by 1 plus z inverse. So this is s, okay. What is this? It is the relation between s and z. Okay. In impulse invariance method, we had used z is equal to e to the power st. Okay. And but here we use this function. So the mapping from s plane to the z plane can be obtained as s is equal to 2 by t 1 minus z inverse divided by 1 plus z inverse. Okay. So this relationship between s and z is known as bilinear transformation. Okay. So s is equal to 2 by t z minus 1 by z plus 1. Now we can slightly represent that z is equal to r into e to the power z omega, j omega, okay, and where we can write s is equal to sigma plus j omega. Okay, so here we just expressing this way, that separating out the real and imaginary part from the right hand side, okay, right hand side of the equation. So and comparing this s is equal to sigma plus j omega with the terms of right hand side of the equation with real and imaginary part. So we get s is given by this, okay, this big expression, and sigma s is this. So sigma is equal to this part, real part, and omega is the imaginary part. Omega is equal to 2 by t. So this omega, you see the frequency. Omega is what is the frequency variable. Okay. So so we find that now what happens, that if r is less than equal to 1, okay, r is less than equal to 1, so what happens, sigma is less than equal to 0. R is less than 1, r is less than 1. So in this equation, that means unit circle, r is what, it's the unit circle, radius less than 1, okay. So sigma would be what, sigma would be less than 0, okay. r अगर 1 से कम है तो ये नेगेटिव हो जाएगा, है। r अगर लेस देन 1 है तो ये नेगेटिव हो जाएगा, और वन अगर r 1 से ज़्यादा है तो सिग्मा पॉजिटिव हो जाएगा, और r अगर इक्वल टू 1 है, r अगर इक्वल टू 1 है तो सिग्मा हो जाएगा 0। So sigma is equal to 0 means j omega axis of the S plane. Sigma plus j omega. Sigma is equal to 0 means j omega axis. Now, so mapping occurs suitably left half S plane, that is sigma negative. Sigma negative means left half S plane are mapped within the unit circle. Sigma greater than 0 means positives are mapped outside the unit circle, that is r greater than 1. And sigma r is equal to 1 means onto the unit circle, that is sigma is equal to 0. Uh, so when r is equal to 1 and sigma is equal to 0, that time, yes, r is equal to 1 and sigma is equal to 0. So what happens that in this equation now, you see omega is equal to 2 by t, and r, putting r value of r is equal to 1, so we get 2 sine uh, r is equal to 1, so 2 term 2 in the numerator and denominator will cancel out. Okay, r is equal to 1 means the there will be 2 plus 2r in the denominator, those will cancel out, and it will become sine omega divided by 1 plus cos omega multiplied by 2 by t. So this 2 by t, now just writing this way, that 2 into sine omega by 2 into sine omega means what? 2 sine 2 theta means 2 sine theta to cos theta. So sine omega by 2, okay, sine omega by 2 into cos omega by 2 divided by 1 plus cos omega means what? 2 cos square omega by 2. So this cos omega by 2 will cancel out, okay, and we will see that it is 2 by t into tan omega by 2. So this omega, yes, this capital omega is now 2 by t tan omega by 2. That is the important concept. So what does it mean? It is the relation between analog frequency and digital frequency. Okay. Or if you take this one, okay, that omega is equal to in terms of the digital frequency in terms of analog frequency. Okay, so this omega is will become 2 tan inverse omega t by 2. Okay, this is actually used because your base filter is in the analog form. Okay, is in the analog filter form. So uh, that is capital omega. So this formula you should keep in mind always, that omega is equal to 2 tan inverse omega t by 2. Okay. So now what happens that so this is a non-linear relation between the both frequency, that is analog frequency and digital frequency. So let us look let us see that when it is written that uh, omega, capital omega and omega are the frequency variables for analog and digital filter respectively, and this capital omega is now 2 by t tan omega by 2. So now in this case, for small value of omega, what happens for small value of omega, that is low frequency? So it is 2 by t into omega by 2 or omega by t. So that means it is omega is equal to capital omega into t. So one is analog frequency, capital omega, and small omega is digital frequency. Or it is similar as f by fs. Digital frequency is equal to continuous frequency divided by the sampling frequency. T is the sampling interval, 1 by fs. So this is coming to be linear equation, okay, for low frequencies. But for high frequency, it is actually this kind of graph. Okay. So you can see here for high frequency or large omega, okay, we see that graph of tan inverse graph, that is this type of graph is the nature of tan inverse. So it is a 2 tan inverse omega by 2. So graph of 2 tan inverse omega by 2 is looks like this. So if you see the positive frequency side, okay, then it is for small omega. Okay, for small omega it is linear, but when omega is large, then that time it no longer remain linear, it is warped. Okay, it is slightly distorted or warped. Okay, so because high frequencies are also getting mapped. So this warping, actually what, there is some drawback in of this warping. You can see from the graph that suppose in analog domain there are multiple pass bands. Okay, multiple pass bands. So for small frequencies, the pass bands does not get distorted. In this small frequency range, it is same, it is not getting distorted. Here also it is same, not getting distorted because linear nature. But for high frequency and very high frequency, we see that the digital frequencies are constricting. Okay, it is shrinking. The band or pass band is shrinking. Okay, so uh, this is one drawback in this system also, but that can be overcome easily. That I will explain. Okay, so this effect is called warping effect. Okay, warping effect. So this is the basic concepts, mathematical equations. Now to remove the warping effect, okay, pre-warping is done. Pre-warping means previously setting the omega p and omega s from the relation this. Now it is better explained in another slide. Okay. In another slide, let me explain this one. So expect effect or disadvantages of frequency warping. So what example is there? Let us say we have to design a digital IIR filter of cutoff frequency 500 Hz and sampling frequency 10 kilohertz. So FC cutoff frequency is 500 and FS is 10 kilohertz. So omega C is what? 2 pi into FC, capital omega. So 2 pi into 500. So it is becoming 3141.59. And digital frequency is omega C, small omega C is F by Fs. Okay. So it is or omega capital omega C into T, capital omega C into T. Okay. So it is in terms of omega, it is coming 1000 pi. Okay, it is 500 500 hertz. So 2 pi into 500, 1000 pi divided by 10 into 10 to the power 3. Okay, 10 to the power 3. So it is how much? It is 10 to the power 3 will cancel out. So it is becoming 0.1 pi or 0.3141 pi 59. So you see that this is the required cutoff frequency. Okay, according to the linear relation between analog frequency and digital frequency. Okay, linear relation when your so difference, you see the difference. This is the now you see this is the analog frequency in radian, that is 3141, and digital frequency in radian is 0.314. Okay, now according to this bilinear transformation, what should be the digital frequency? The digital frequency is 2 tan inverse omega c t by 2, according to the formula. Okay, this formula 2 tan inverse omega t by 2. Okay, So you use the formula 2 tan inverse t by 2. So you put this value in place of omega c, digit analog frequency is this, and time this uh, omega c into this frequency, okay, that is omega c into t, that is 10 to the power t, that is t is 1 by fs. Okay, so it is 1 by fs, 10 kilohertz is there. So 1 by 10 is 1 by 10 is zero point 0.1, and kilohertz is 10. 1 by kilohertz means 10 to the power minus 3 is there at the top, at the denominator. So here by 2. So this way we get 0.3116. Okay. So mapped cutoff frequency after bilinear transformation. So, but actually it should be 0.314, 0.3141, but actually it should be this one, but due to warping or due to the bilinear transformation, it is getting reduced. It is becoming 0.3116. So omega c, okay, desired, this is desired 0.314, but we are getting 0.3116. So this is the drawback, or this is the effect of frequency warping. Okay, so we cannot design an accurate filter with the same frequency requirement. So to avoid this, to overcome this, we use pre-warping. Okay, what is pre-warping? Now you just go through these lines, that you can remove the warping problem using a simple technique. All you have to do to get a digital IIR, why it is called IIR? Because it all deals with poles. Okay, IIR system has poles in its transfer function. Okay, in its impulse response. In all the discussion, you see poles are there. So that's why it is IIR filters. The numerator by denominator. Denominator is of there. That means poles. So, so what we have to do to remove the effect of warping? That all we have to get a digital IR filter with the same desired cutoff frequency as omega c. Okay, is to design an analog filter with a cutoff frequency that maps to omega c after bilinear transformation. So we call this process pre-warping. We need to pre-warp the analog filters. So look at the graph we have above. The blue line that is tan inverse graph represents the frequency response after bilinear transformation, and the red line represents the linear characteristics of omega and omega, small, capital and small, to obtain the expected response, which is the red line. Okay. So uh, to obtain the expected response, which is the red line, this is the linear is the red line requirement. We are going to merge the blue line with the green line so that it cancels out and gives us the red line. This is basically what pre-warping does. So how actually do we calculate this? So with bilinear transformation, what relation we get? That is capital omega is equal to 2 by t tan omega by 2. So this is the opposite relation. Tan inverse is for the converting analog frequency to digital frequency. Here this equation is just written oppositely, that the analog frequency in the form of digital frequency. Omega is 2 by t, tan omega by 2 with bilinear transformation. Now during pre-warping, what we do? We do actually 2 by t tan omega c by 2. Okay, because say we set some cutoff frequency, okay, required cutoff frequency, we just change the value. So by using this method, so pre-warping is done this way. Okay. So now, so let us take one example. Okay. Let us say omega c is equal to zero point 0.1 pi. Okay. Omega c is equal to zero point 0.1 pi. That is the desired cutoff frequency. Pre-warp cutoff frequency is 2 by t tan omega c by 2. So we get this value 3000 something. Now this is the value that we design the analog filter with. So omega c is now 2 tan inverse omega c pre-warp into t. So that means you see that tan inverse and tan both will cancel out. Okay, tan inverse into tan. Okay, tan inverse of tan, it will cancel out. Okay, so that is the main concept. So it is 2 tan inverse this one, so it is 0.15. So this is the pre-warping effect. Now let us see one example. Okay. No, what is the steps? So first step is steps to design digital filter using bilinear transformation. So find pre-warping analog frequencies. So there are two frequencies, that is stop band and pass band, okay, omega c and omega p. Okay, and uh, then you find the transfer function h of s of analog filter. Then select that sampling interval t, okay, and substitute s is equal to this one 2 by t 1 minus z inverse divided by 1 plus z inverse. Now let us see one example, that design a Butterworth filter satisfying the constraints, that AZ is uh, magnitude of the digital filter is within 0.707 to 1 for omega. Okay, next, today I think you'll not understand this problem. Okay, next day we'll discuss tomorrow. Tomorrow we have class. Okay, so by the timing you go through the theory. Okay. So tomorrow also we are having quiz. Are you aware of it?
Yes, sir.
Okay. So I am now stopping today. Okay. Next day we'll explain the example. Then it will be better clear.
Thank you, sir.
Okay.